Alright, in this video we do an example involving the power triangle where we're going to find the power triangle values along with the power factor for the load in this circuit where we have a 230 volt source at 0 degrees connected to an impedance load of 10 plus J3 ohms, and in between we have some line resistance, this 1 ohm represented by this 1 ohm resistor. So a good place to start in this problem is just to draw out the impedance triangle, okay, where this is theta z, and we have a resistance, a real part of 10 ohms, and a reactance, an imaginary part of plus J3 ohms. So that's an X of 3 ohms on the plus J axis. So we can find the magnitude of z, the hypotenuse of this right triangle, by just taking the sum of squares, square rooted. So we'd have the square root of 100, right? 10 squared plus, 10 squared, which is 100, plus 3 squared, which is 9. And then the square root of 109, which comes out to 10.4. Okay, so that's our z here, the hypotenuse, the length of the hypotenuse is 10.4. Okay, and as we discussed earlier, theta of the power triangle, if we write the power triangle down here, right, this theta is the same theta as theta z, right? In the power triangle, P average is the adjacent side, Q is the opposite, and then apparent power is the magnitude of the hypotenuse. So as we discussed earlier, these triangles are, the impedance triangle and the power triangle are scaled versions of each other, so the angles are the same. So theta of the power triangle is the same theta as theta z. So we could just find theta of our power triangle by just doing theta z, which is inverse tan of opposite over adjacent. So just inverse tan of 0.3, which will come out to 16.7 degrees. Alright, and then power factor, which is one of the things that we'd like to find here. Well, power factor of the load would just be cosine of that angle. Okay, so cosine 16.7 degrees, and that comes out to 0.958, and then it's lagging since this is a positive J, that's inductive, and inductive power factors are called lagging power factors. Okay, so always remember with power factor to label whether it's lagging or leading. Just to write 0.958 without the lagging is not complete, so make sure to include that. Alright, well now to get P average, one way to do it is we can find the current flowing through the load and square that, and then multiply times R of the load. Okay, this 1 ohm resistor does not come into play here for the resistance because we're getting these values, these power triangle values for the load, so you use the load R. However, as you'll see, when we calculate the current that's flowing in the circuit, well, then we include the 1 ohm resistor because it's part of the path of the current that flows through the load. And then Q is just I squared, this is a tilde, okay. Reactive power is just I squared X, and then one way to get apparent power is just to do I times V for the load, or what we can do to get this is we can find S by just taking P average and then plus Q, right? And then we just do sum of the squares to find the magnitude, because this will be a complex number because P average is real, Q is imaginary. So then we can just find the magnitude of this complex number, S being a complex number since it's complex power, and then that will be our apparent power. So what I mean by this arrow is that once we have this, then we can use this to get the magnitude, and that's our apparent power. So let's go ahead and calculate these power triangle values. So first we need the current that's flowing in the circuit. So that current is just going to be the source value, the 230 at an angle of 0 degrees, plus the total impedance, which is going to be the 1 ohm plus ZL. So we're going to have 11 plus J3. Right, so you see this is just voltage divided by impedance, okay, which gives us current, as you know. So to do this, okay, I changed this rectangular complex number into polar form. So if you do 11 squared plus 9 and then take the square root of that, it comes out to 11.4 as your magnitude. Okay, and then the angle is going to be inverse tan of 3 over 11, which is 15.25 degrees. Okay, so our current is just 20.2. That's 230 divided by 11.4, 20.2, and the angle is just 0 minus 15.25 degrees. Okay. So now P average, okay, the length of that adjacent side of the power triangle is just going to be this current squared times the resistance of the load, which is the 10 ohms. And if you do those numbers, it comes out to a P average of 4,080 watts. Okay, and then Q is going to be the same current times the reactance, which is 3. So that gives us a Q of 1,224, and then the units of reactive power are VARs, like we've talked about. Okay, so now S, the complex power, is just P average along with Q, okay, the units being VAs, volt amperes. And now to get apparent power, well, I just do the square root of sum of squares, so 4080 squared and 1224 squared. Alright, so you work out those numbers and the apparent power comes out to 4,260 VAs. So you see here are the sides of our right triangle, the adjacent side, the opposite side, and then apparent power, that's our hypotenuse. So if you go back and look here, the P average, that's the 4,080 watts, the Q, that's the 1,224 VARs, and the hypotenuse here, apparent power, that's the 4,260 VAs. So that wraps up this problem, and we will do some more AC power analysis discussing a very important application called power factor correction, and that will be the next couple of videos.